Welcome to The Explainer. Have you ever wondered why so many things in life seem to just naturally cluster around an average, with those wild, extreme outliers being incredibly rare? Well, today we're going to unpack exactly how the universe organizes data by breaking down the anatomy of a very specific, very powerful shape. Let's get into it.
Here's a quick roadmap of what we're covering. 1. Continuous versus discrete distributions. 2. Shaping the normal curve. 3. Rules of the bell curve. And 4. The power of z-scores. All right, Act 1, the foundation. Continuous versus discrete distributions.
To build a solid base, we kind of need to look at what continuous probability is not. Think of discrete data like rigid building blocks. It's information that fits neatly into tables. But continuous probability? It's fluid. It absolutely cannot be expressed in a simple table. You need an equation for it. And what's really mind-blowing here is that because continuous data has literally infinite possibilities, the probability of pinning down one exact, infinitely precise point is actually zero.
And that brings us to the absolute star of the show, the normal distribution. Often called the Gaussian distribution, this is easily the single most popular, most useful continuous probability distribution for any random variable, which we'll just call x. This concept is a total game changer. It fundamentally shifts how we understand probability, giving us a highly reliable way to describe really complex continuous data using just a couple of key parameters. Moving on to Act 2, the architects of the curve. Shaping the normal curve.
So there are two specific parameters that act as our master builders, controlling exactly how this curve looks on a graph. The first architect is the mean, represented by the Greek letter mu. Think of it exactly like a steering wheel. It completely determines the location of the center of the graph. If you change the value of the mean, you simply shift the average, the center of the normal distribution, to the left or to the right along your axis. But notice this, the overall shape of the distribution stays exactly the same. You're just driving the curve to a new location.
Then we have our second architect, the standard deviation, represented by the Greek letter sigma. Now, if the mean is the steering wheel, the standard deviation is the gas pedal and the brake. It dictates the actual height and the width of the curve. By altering this value, you are fundamentally changing how the data is spread out from that center point we just established. Here is the really crucial takeaway. As the standard deviation gets smaller, the curve gets much steeper because all the data is tightly packing together. Conversely, when it gets larger, the whole distribution flattens out and the data spreads far away from the center. Act 3, the golden rules. Rules of the bell curve. Once those architects draw the curve, it has to follow a strict set of laws. First up, because the curve is perfectly symmetrical about the mean, median, and mode are all exactly equal. They sit dead center. Second, the total area under this curve always equals 1.00, or 100%. That represents all possible probabilities. And third, the curve is asymptotic. That's just a fancy way of saying it gets infinitely close to the x-axis on the tails, but it never ever actually touches it. It's kind of like an awkward high school dance, where you just hover at the edge of the floor all night. Now, to actually use this shape in the real world, we've got to chop it up. The normal curve area is essentially subdivided into standard scores, stretching out to the left and to the right of that vertical center axis. Along that horizontal line, the distance from one integral standard score to the very next is measured perfectly by our old friend, the standard deviation. Let's see how the data actually falls into these subdivisions. Following those strict rules of symmetry, right, around 68% of all data values in a normal distribution will lie within just one standard deviation on each side of the mean. So right there in the thickest part of the bell curve, over 2/3 of your data is just sitting comfortably. Push it out just a bit further to 2 standard deviations on each side of the mean, and suddenly you capture approximately 95% of the data values. We are getting really close to capturing absolutely every possibility.
And if you go out to 3 standard deviations, you've captured 99.7% of the data. Almost everything in the entire distribution lives within these 3 standard deviations. It is a highly predictable structure for dealing with entirely unpredictable random variables.
Act 4, the universal translator. The power of z-scores. To reach true mastery here, we need a mathematical universal translator to standardize our data, and that is the z-score. You should treat this formula like a profound quote in the world of statistics. Z equals x minus mu divided by sigma. What this formula essentially does is shift the mean of your observation, x, to 0, and then it changes the shape of the curve to give you a standard score, z.
It puts everything onto one standard scale.
What's really cool about this is just how simple the inputs are for such a heavy lifting tool. All you do is take x, which is the value of your particular observation, subtract the mean of the distribution, and divide by the standard deviation. By doing this, you instantly translate your specific, unique piece of data into a standardized z-score.
All right, so once you have your z-score, finding the actual probability is a total breeze using a z-table. It's just a simple three-step process. First, go to the row that represents the leading digit and the first digit after the decimal point of your z-value. Second, jump over to the column that represents the second digit after the decimal point. Finally, intersect the row and column, bam! That intersection number is your exact probability. You've successfully translated raw continuous data into a solid, usable probability.
I'm going to leave you with this thought as we wrap up this explainer today. If a single mathematical equation can organize the absolute chaos of continuous random variables into perfect, elegant symmetry, how does predicting the unpredictable change the way we view the world? Mastering normal distributions doesn't just help you pass a statistics class, it fundamentally upgrades the entire lens through which we interpret the vast, unpredictable universe around us. Thanks for exploring this with me. Keep questioning the data, and I'll catch you on the next explainer.